Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I would like to talk a bit for some period of time. Right, so intrinsic image decomposition I will talk about a bit, but I realized actually only like about 10 minutes, so I do some other stuff as well, which I'm going to start with. So just a bit of advertisement. So with Rhemann, you see here a very small picture, we had this idea of starting a new virtual group in the which is a lot of the vision people are involved, and a lot of the people from the CML group, that's like human-computer interaction group. So we thought about joining forces on some topics to get bigger things done, like bigger SIGGRAPH papers. So some of the things we work on is, so we look at cameras, we look at time of flight camera, and we look at various other cameras, building our new cameras for various applications. So the applications are like Reality Remix is one, so that's like probably you know the Kinect Fusion system. And there's actually, this year is an extended version of Kinect Fusion where we actually go outdoors. So we build our own stereo camera and we go outdoor and do real-time 3D reconstruction. And then you can do a lot of augmented reality with it. The part I'm most excited about and we'll talk a bit about today is going with such rich input, going further and, for instance, do decomposition into shading and shading properties, shading shadow properties and material properties. But also, for instance, if you have some stereo set up, you can estimate 3D bounding boxes and physical information from it. And from this physical information, hopefully to loop back to scene understanding with richer input. And then that's Jamie talked about this work mainly, and he's driving a lot of that, but that could be potentially combined with some Reality Remix, is deformable objects, and that's a great body of work. And like here's like an image of an older SIGGRAPH paper we had on deformable in video. Okay. So before I start with the main talk, just like another paper we had at last BMVC, which I think is a quite interesting paper, and I mention it because we actually currently work on a new submission for BMVC again to try to have a bit more theoretical grounding on this work. This is a very simple algorithm. I'm not sure how many people have seen about the PatchMatch algorithm, PatchMatch work. So we used it in the not traditional sense where most of the time PatchMatch is used. So in this work here, which was last BMVC, was so typically what people do with stereo matching, they have two cameras, so it should actually be two cameras down here. What people use is, so the green is the true surface, and people typically have these front to parallel depths, so they have discrete depths, and also their support windows when they do matching are front to parallel windows. So this green surface here, you could either have a matching cost here at this particular depth or at this particular depth, right? So in this work here we said, well, we would try to do a matching. It's pure unary terms, it's just matching of support windows, where the support windows are orientated in 3D and have continuous depth. And obviously that will support the true surface much better. So this is the reconstruction here with front to parallel, and this is what we get when we align the windows. And this is actually, there are no pairwise terms in here, and that's currently one of the things we're looking into, how to put in pairwise terms. So now, so the main challenge is how to actually get these. So these planes can be represented, these support windows, by three continuous variables. At each pixel, how do you optimize them? So we use this PatchMatch algorithm, and the main idea is that first of all, quite often there are like bigger planes in the image, or even a bit, I mean, if it's a bit curved, it might also still work. But there are larger regions which are supported by one plane, like this image here, for instance. And the idea of the algorithm is just to say, if you have on one plane, if you have one pixel where you've got the right guess, you can propagate that information. And I will come to the algorithm in a second. So that's the whole idea. If you have three correct guesses for this image here, and here, and here, and here, you can actually very quickly propagate it and get the right solution out. So the algorithm is extremely simple. You randomly initialize the plane parameters. So there are 3 parameters for the plane, the continuous parameters. Then there's a propagation step, and I will come to that point in a second. But it feels the ingredients are very similar to belief propagation or particle belief propagation, which we currently look into. And we try to make exactly the correspondence and see if there's something to be gained when you actually express it as a particle belief propagation. But anyway, so what this algorithm is, the PatchMatch is simply doing is it's doing propagation. So it's like it says it has a solution. For instance, here we've got 2 actually labeled both images with terms of depth. We have, for instance, a solution for this pixel here and for this pixel here. Now we try to find the solution for this one here. So this is the random initialization. What we simply do is we look at the neighbors and say, is it a lower value? Is it my unary cost if I recompute it with that particular ABC coordinates or these ones? Is it a lower energy or not? And then you take it, or if it's high, you don't take it. If it's lower, you take it. And that's all. You simply propagate. There are also some more interesting propagations across views. When you've done, you can actually propagate into the other, and also temporal propagation for videos. And then there's a random sampling step in there where you have the solution and then you actually refine it, or you sample it around your current solution. And it's just kind of, you think about a Gaussian surrounding localized on your current solution, and you sample from that to refine it. We totally do 3 iterations. And so as I said, we currently look into how this actually can be expressed as particle belief propagation, and pairwise terms potentially could be put in. And I think it's going to be quite interesting, hopefully good submission to BMVC. Anyway, so here is the short video. It's running here. Right, so random initialization, and then this is simply propagation of top left to bottom down, and you already see it's quite good. Then it's going the other way around up. In between there are refinements, which I'm not sure if they're visualized, and then it's going down again, and then I think it's finished. There are 2 more quite standard steps of checking left-right check, and then filling in the pixels which didn't satisfy this check, and then this is the output. So we actually managed to put that on in real time on several GPUs, and we had these results I showed in the beginning on 3D reconstructions in real time that was actually done with this method. So just some results. So especially these nice slanted surfaces and curved surfaces are done pretty accurately. And there are no pairwise terms in here. It's just purely unary terms. So here it's just a demonstration about if you were to use integer, then you get these steps, which you see here. The next thing is integer but orientated surfaces. And the other one is continuous depth and orientated surfaces. And you clearly see the improvement.
Have you tried those scenes with people?
We haven't tried people, no. Well, no, there's a video coming in a second, but no, I don't recall any images with. So you clearly see improvement in terms of depth estimation. Yeah, there's one here on the stereo video. And as we said, we managed to put that now into real time with several GPUs. Okay, so main topic of the talk. All right, only 7 minutes. Okay, so this is a NIPS paper which we had last year. So intrinsic image decomposition. The goal is you have an input image. You try to separate one image into 2 images. One is only on the material, and the other one is on all the light effects, which is shading and shadow. Very ill-posed problem. And so currently in our approach, we ignore specular highlights. So we phrase it as in the following way. So there are 3 color channels. For every pixel index I, we have to compose it into the shading shadow, which is small s, because it's just one-dimensional. And this is 3-dimensional, is the reflectance for every pixel. Okay, so motivation is in general interesting problem. Would be great if it works perfectly. Would be great to have as inputs for shading, recognition, potentially a segmentation, and so on. So I think it's quite interesting, but obviously it's a very hard problem. I mean, that's going to be in my outlook. That's we're currently looking into, like in the Kinect Fusion sense, like if you have some rough 3D reconstruction, how much better can you get? But currently in this work, we do it with a single image. We see how far you can get. There was one paper, for instance, at SIGGRAPH 2 years back, 3 years back, which did interactive. So you had some scribbles. Additionally, you get this reflectance out, this shading out. Here they used they had colored shading image because there might have been multiple different lights with different colors. They can then just do this image editing with it of putting some different texture on, and they have to warp the texture as well, I guess. But they put all of the shading shadow from this image on. Okay, so there is a certain database, but the main problem is it's not very big. This is the database. So people from Rhemann, from the US, they have done that with it's quite elaborate setup. So they have a table where they put an object on, then they photograph it, and then they actually move out the whole table with the object on. They spray it in white, and they move it back in and take another picture. I'm not sure about the alignment, how good that is. So these are some of the objects in there. And these are the decompositions, which is the ground truth. They measure, I have to say that I'm not sure about the quality of the ground truth. You really zoom in, I think there's more noise than there should be. So these are some of the decompositions. So our formulation is, so first of all, you can reduce the problem to one unknown parameter because you have this equation here, which are 3 equations for each color channel and 4 unknowns. So the S is one-dimensional and 3-dimensional for R. So four unknowns per pixel and 3 equations. So you can rewrite it in a small r. So one scalar for each pixel is the unknown variable. So basically, this is an R tilde which can be pre-computed, and this is the true reflectance multiplied with an R, and this is the shading. This is the norm of the intensity. So if you plug Si and Rc in there, you get out that I is equal to I, so it's satisfying the equation. Okay, so what we do is a conditional random field with 2 standard terms and 1 new term, and then we just see how it performs with this new term. So the 2 standard terms are the shading and the so-called color Retinex term here, and this is our new term called a clustering term. So the shading term, sorry, is a very standard term, which is just a smoothness term. You have the shading here, and you say neighboring pixels should have the same shading, and it's just a quadratic norm on that, quadratic penalty. So these are crops of the real image. Here it's pretty smooth, but here it's not very smooth, so it's not always very satisfied. So this is a new term. What we have is the idea is that the image is only composed of a few reflectances. So this is the reflectance image, and this is the input image. So these are all the colors here distributed from the image, and this here is from the reflectance image, and you see there are more clusters here. So this is the white cluster, and these are the different colors here. There are some in-between colors that come from these transitions here between the strokes. So the whole idea is to say that an image has typically a few number of reflectances. So we try to find out what are the reflectances, what are these clusters, what are the color of the clusters, and how is the clustering done, and at the same time solve these other parts of the energy. So this is the cluster energy, which we try to find the, we have k clusters, and I come to that in a second. We try to find the color of these clusters, and then we say the true reflectance should not deviate too much from the reflectance of the clusters. So this is the illustration about the power of this clustering. So here is an input image, this is the decomposition. This is the clustering if it were to be perfect. If there is no smoothness on the shading, so this is just smoothness and the clustering. If there's no weight on the smoothness, what you see is that within a cluster you actually get the perfect shading out, because within a cluster it has to explain everything by the shading. Now across the clusters you don't get a nice result, and then if you switch on just a bit of smoothness, it basically says between the clusters has to be smooth, and you get the nice result out. So this then, with a bit too much smoothness, you get over smoothing here. So the interesting bit is even if you have a lot of over-segmentation, there are only, in this case, probably 50 clusters, you still get out a quite nice result with a bit of smoothness because these pixels are all constrained. Within the cluster here, it's getting out the right result. So as long as there are some pixels which are clustered correctly, you get out within the cluster the right thing, and the rest is done by smoothing. So the last term is the standard term gradient consistency, which is the basic thing of color Retinex. What you do is you first classify the edges if it's going to be a reflectance or shading edge. So this is the clustering here where you hopefully correctly classified it. And then you just say you know what the jump is in the reflectance that's taken from the image here. And then you just put that energy in, that in the final result you want to have the same jump in the reflectance. So here's just for the color Retinex an illustration what you typically get out. So you have got these classification here. This is black is a transition. So you have these transitions, and you know how strong the transition should be, and you can get these reflectance images out. And this is the shading image. Right, run a bit out of time. So this is the algorithm. It's basically just iterating between the reflectance computation and the clustering. So it's just like we initialize the clustering k-means, and then we also optimize this R, and then we cluster again, and we optimize R. So here is the results with cross-validation, just to show that that it actually improves when you have our full model. And these are comparison to state of the art. So this is our model, and these are kind of like competitors, various competitors. When you've used multiple images, that's the Weiss method. They're still better. But yeah, this leave one out, cross-validation. So here are some results. I think the main thing to take out is when we use our full model, the results look much more, and the reflectance looked more realistic. So this is like color Retinex with our global term. It looks visually very different to this one here. And here's another one. So this is color Retinex. And this the full model is like it's much smoother result than with color Retinex. Okay, so next steps we might look at different priors. We look at different input stereo connect fusion applications, interesting potential recognition, and where to get training data from, real versus synthetic. That's kind of another interesting question. Okay, thanks a lot. Andrew, do you have a question? No?
Well,
Did you see it at NIPS, the paper?
I hadn't, thank you.
Okay.
I'm going to read it. Maybe the only question I was thinking, when you're showing the results, is there's still some residual in your final results.
Sure, like an error, you mean, yeah.
Yeah, so what's the cause of that? Is it your model's not matching? Have you got extra smoothness?
Sure, I mean, like texture, I think. Texture objects which are highly textured, fur and things like that is very hard. There are interreflectances, all different difficult things going on there. I think if you have very simple objects like a whole same reflectance on the big surface, that's relatively simple. If you have a lot of like here wood material, it's also not. Well, I think that's okay. We start to think a bit about different priors for reflectance, like field of expert prior or things like that, but we haven't trained that yet. The thing is, like, the student is a very good student, a lot of like machine learning skills. He kind of says the database is so small, it's like he could overfit it and then get, but he doesn't want to overfit. And it's just like a small training database. I think where to have a big training database would be good. Obviously, it's not out there. I mean, normal images you cannot really take. So where do you get data from? That's the problem. You could think about just using that, I don't know, probably from photosynth I was thinking, because there's some, I don't know, I had some ideas to think about training data in a, like, not as elaborate way as what they have done, but that's an open question.
You mean graphics as well? You can of course do.
Yeah.
You want to.
Yeah, but we started to do a bit on graphics, but they didn't look realistic enough, the images yet. And that, I very much believe in graphics. I mean, what Jamie has done is graphics, but only for depth cameras. If you have for real cameras, RGB cameras, I think that's an open question. Is it realistic enough for RGB images?
Right.
Okay.
We have to move on. Thanks, Carsten.